Frank-Wolf or conditional gradient with projected gradient for a constrained lasso problem. And I'm just counting iterations. So I'm not considering the fact that a projection onto the L1 ball is more expensive than that very simple Frank-Wolf update, which just looked, to remind you, just looked at the maximum absolute component of the gradient and then moved in that direction. So it's more expensive. They're both order n. I'm just counting iterations here. We can see that the Frank-Wolf method in red converges a lot slower to high accuracy than projected gradient. And this is a log scale, so after 1,000 iterations, we're still like, the gap between f and f star is still somewhere between 0.1 and 1, whereas projected gradient is like 0.001 or smaller. So it's a lot slower to converge to high accuracy. That's not as, this is not like an oddity of my setup. This is something that I found to be pretty consistently true in practice, and I think that's the consensus, is that Frank-Wolf methods, they have very cheap iterations, but they're on the other side of gradient method than Nunes method is, and that they take even longer to converge to high accuracy. So if you think about the full hierarchy, we have gradient descent, which is cheap, converges to high accuracy fairly slowly in the grand scheme of things. Nunes method, which is more expensive, but converges a lot more quickly. And then Frank-Wolf, which is very cheap on the other side, but makes kind of very incremental progress towards high accuracy solutions. So we're going to go through a few guarantees for Frank-Wolf. I could cover the proof of its convergence rate in detail, or we can just move on to some extensions. Maybe at this point in the class, since we've done careful analyses here and there, I'll just talk about the extensions, and I'll let you read the Jaggi paper if you're interested in the proof. But there's a bunch of kind of useful things that you could to learn about before you implement Frank-Wolf for your favorite problem. Because sometimes, some of these extensions like step size optimization could make a big difference. In this case, I just used the fixed step size rule. It would probably be better if I'd used some step size optimization. But actually, for both methods, I just chose a fixed step size. So Frank-Wolf iterations admit a very natural duality gap. And in truth, it's really just a suboptimality gap. It's a gap that's a bound for f minus f star. And that's the following. Just the max over all points S in my constraint set C of grad f transpose x minus s. Okay, and so let's look back at our update rule. Our update rule looked like the minimizer of grad f transpose s over all s in the point C. Suppose that minimizer I just call sk minus 1. This max, I just get by taking grad f transpose xk minus 1 minus sk minus 1. So I get that right out of my Frank-Wolf iterations, because I can split this up into two terms. The first term doesn't depend on s. The second term is max of minus s transpose grad f. That's obviously attained at the minimizer of grad f transpose s, which I've already computed to make my update. So this is an upper bound, it turns out, on f minus f star. And the proof is basically on the slides, plus a few details I left out, but it just comes from the first order condition for convexity. So I just say that by definition of convexity of my function f at the point xk minus 1, I have the property that for any s whatsoever, f of s is bigger than or equal to f of xk minus 1 plus grad f transpose, that should say s, that y should say s. Right, that's just a typo. So I guess in both spots I had a y here. That should just say s. Okay, and this is true for any s by convexity. Minimize now both sides over all points s in my constraint set C. I get f star, the minimum of f over all points in the constraint set C. Minimize this over all points s. Well, this term doesn't depend on s, so it comes out. This term is exactly the minimum over all s in the set C of the same criterion we had up there, grad f transpose s minus xk minus 1, just it's the minimum of the negative quantity up there. Okay, and so if we just rearrange, just move this to this side, and move f star to this side, and just suck in the, when I move to this side, I get minus the minimum of something. I'm going to suck in the negative sign and just have maximum of that something. I see just exactly that this quantity I have written up there, maximum of grad f transpose x minus s, is less than or equal to f minus f star. Yeah, John?
What is that y?
Sorry, all of these y's, let me just write it down for you. All these y's are supposed to be s's. It's just a typo. Okay, that's what is meant. It's just supposed to be, and then if we minimize over s, we just get f star bigger than or equal to f of x k minus 1 plus and then if we just rearrange, that's what I was saying, you get minus the minimum of grad f transpose s minus xk minus 1 is bigger than or equal to f of xk minus 1 minus f star. Okay, so this is an upper bound on f minus f star, and if I just suck the minimum inside, I get max of that quantity. So as we're running Frank-Wolf, we could stick in another step, right after, say, in between these two updates, so right after the first one, which checks the duality gap and terminates if it's less than epsilon. That would be a pretty rigorous way of stopping. Okay, how about convergence results? So there's a result for Frank-Wolf, or the conditional gradient method, that's very much like what we have for gradient descent. It just assumes something a little different. And it assumes something about what's called the curvature constant of our function f over the set C. And we're going to see that this is actually very much connected to assuming that f is Lipschitz, grad f is Lipschitz over the set C. So just like what we would assume for gradient descent. But ignoring that for now, let me just tell you the result. The result is that if I use fixed step sizes, and I have some condition on my function called, it has a curvature bound, and m is what's called the curvature constant, then after k iterations, I get that f, my function f at the point xk minus f star is less than or equal to 2m over k plus 2. So its convergence rate is like 1 over k, or in epsilon notation, it's like 1 over epsilon. To get an epsilon suboptimal solution, I need 1 over epsilon iterations on the order of that. Okay, so this is the same vanilla rate we derive for gradient descent. So let's break this down a little bit more. What is this m? This m is the difference between f and its linear approximation over all points essentially over all line segments that lie within my constraint set C. So let's draw ourselves a picture. Here's my constraint set. What I do is I take x and s, and I look at all points that lie in the line segment between x and s, and I call that such a point y. And remember, Frank-Wolf makes updates that look like this. Right? This is my proposed new point. This is where I am. I update in the direction of s by some amount. And we'll call this point, it's just going to be 1 minus gamma x plus gamma s. And what I'm looking for when I'm defining this curvature constant is along this line segment, what is the biggest discrepancy I have between my function f at y and a linear approximation to my function around x. So first order condition for optimality, for convexity, tells me this. Right, I know that's true. In other words, I know this is true. But now the question is, what is an upper bound on this quantity? Okay, how big can this quantity be? Overall points x, s, and y of this form in my constraint set. That is precisely what the curvature constant is measuring. Okay, and we just have some scaling here, 2 over gamma squared, that accounts for this choice of gamma. So we're going to see in the next slide this is very closely connected to the gradient being Lipschitz. I just wanted to pause so that you can just digest that definition for a second. Okay. So what we saw was, oh yeah. Kappa? Yeah, sorry. That should say, yeah, this quantity is 0 if f is linear, because we have an equality here then. So we've matched here the rate for gradient descent, but how about the conditions? Are these conditions stronger than we assume for gradient descent? Are they about the same? In fact, they're really no different in a sense from what we assume for gradient descent, or at least they're not stronger. That's what we're going to show on this slide. Let's suppose that that f had the property that its gradient was Lipschitz with constant L. Then, in that case, we're going to show that such an m exists, the bounded curvature constant, and it's going to be less than or equal to L times the diameter of my set C squared. So the diameter is the biggest distance between any 2 points in my set. And if we've shown that, then let's look back at this rate. We can replace this m, if f had a gradient that was Lipschitz, by L times the diameter of my set C. And that is very much like what we had for gradient descent. For gradient descent, we had actually x naught minus x star squared there. Right? But an upper bound for that is just the diameter of my set C, because that's the biggest difference between any 2 points in my set. So this is going to look very much like our rate for gradient descent. So the proof, again, is just on the slides here, just a couple lines long. If we have the property that grad f is Lipschitz with constant L, then you prove this in the first homework, and we've seen this a bunch of different times, that gives us an upper bound on our function. Right? It's a quadratic upper bound on our function. And so in particular, I can actually subtract all the linear terms to one side, and just claim that means that this quantity here, this is actually called the Bregman divergence, my function. This quantity here is upper bounded by L over 2 times y minus x squared. Okay, now if I just plug in for what y was in terms of s, and I manipulate, I can easily upper bound m, because m is just the maximum of all this stuff over all points y, s, and x. Okay, so I'll leave this calculation to you guys to check, because we're kind of closer to the end than I wanted. Okay, but the conclusion is that if grad f is Lipschitz, then we get this condition for free. So it's not any stronger than we assume for gradient descent. So far, Frank Wolf is looking pretty favorable, right? We have cheap iterations. We have very similar theory. And it looks like it's going to be very effective for large problems. I'm going to skip the proof. This stuff is on the proof. I'm also going to skip this. I'm just going to go to a few important properties of Frank Wolf that you may want to pursue. And then I'll just conclude by, again, maybe stressing that in practice it tends to converge a little bit slower than first-order methods. So it's possible to analyze Frank-Wolf under inexact updates. So that means that if suppose I can't find the exact minimizer of my gradient transpose S over my set C, but I can find it up to some constant. So I can find some point sk minus 1 that's within this of the minimum. This is called an inexact update. Okay, maybe you can liken it to, in the world of proximal or projected gradient, doing an inexact projection or an inexact prox operator. And this delta is our inaccuracy parameter. Now remember that gamma is shrinking. So gamma is 2 over k plus 1 or something, or 2 over k plus 2. So this is shrinking. This is telling us that actually, if we achieve this for constants m and delta, then we're actually doing better and better at every iteration. So our inexact updates are becoming closer and closer to exact. So under this condition, we basically get the same rate. The right-hand side is just multiplied by 1 plus delta. And the interpretation is that Frank-Wolf is pretty robust to inexact updates. Okay, and the proof of this is actually not very difficult. It follows from the initial proof quite carefully. I also want to mention two variants of Frank-Wolf. Those are a line search method and a fully corrected method. And I think that people tend to use line search in practice. I don't know of large-scale implementations that use the fully corrective method, but I could be missing something. These are both important variants. The first is that instead of fixing the step sizes according to this rule, 2 over k plus 1, we could do something like this. We could try to find the value of gamma that makes our function the smallest along this line. This is like doing gradient descent with exact line search. It's really the exact same thing. This is the proposed update direction, s minus x. I don't know how far to go in that direction. That's what gamma controls. So let me try to do the best I can along this one-dimensional line. That's how I could update gamma k. So the reason why people don't use this is the same reason as they don't use it in gradient descent. It's just not typically possible to find such a value of gamma. And it's not really worth it to perform a one-dimensional optimization to find it. People typically just use backtracking. Okay, so in place of this, we could just use backtracking like we do in gradient descent. This is now just our direction. So where we had the negative gradient before, we just have s minus x here. So with line search, Frank-Wolf improves, but in my experience, there's still a barrier between it and a first-order method. Okay, so both first-order methods and Frank-Wolf improve with line search, but you still have the property that Frank-Wolf is going to converge slower in practice. Another variant of Frank-Wolf is called fully corrective, and that is the following. Every time that you find a new proposed update S, you actually allow yourself to update your point Y to be anywhere in the convex hull of points you've seen. So, and note this actually includes all the previous x's as well, because x's are convex combinations of some x and some update sk minus 1. So this, if you could do in practice, I believe makes much, much better progress than Frank-Wolf. But it's also quite a bit harder to do. Okay, because now I'm instead of a one-dimensional update, I'm looking at a kind of sophisticated update at every step. This has an interesting interpretation when it comes to L1 methods as well. I'll let you guys read more about that, but if you're interested. But basically what this is saying is that I can update myself anywhere within the support of solutions I've visited so far. Because each one of these will be sparse for L1 updates, and they'll be sparse on a different component that you visited. So their convex hull is going to be like vectors that have a sparsity pattern that is consistent with all the vectors you've seen so far. So I'm allowed to, at any point, I'm allowed to look at all the variables I've touched and getting to the step k, and I can update my optimization variable to be something that's supported on the union of all the variables I've touched so far. So both of these have the same complexity in terms of the convergence rate formally. This one I think is a lot better in practice, but it's just harder to do. Okay. Are there any questions about Frank Wolf? I have maybe one more thing I can talk about, or I'm happy to take any lingering questions. So the last thing I can share about Frank Wolf is there's an interesting path following method with Frank Wolf. I think this is probably the most, to me, one of the most exciting developments in these local linear methods is that with Frank Wolf, you can perform a very simple approximate path following algorithm. So we didn't talk about path algorithms. We're not going to talk about them. We're going to choose to talk about something else. But path algorithm is, roughly speaking, something that tries to solve a problem of this form, but treating t now as a hyperparameter properly, in the sense that we try to track the solution as t varies. So if we start t at 0, then if this is a norm, the solution is just 0. But the question is now, as I let t grow, can I say something more intelligent about the solutions, their evolution, than just solving the problem at a bunch of discrete values of t that I just pick arbitrarily? That's called a path following method. And Frank Wolf can actually be used to drive an approximate solution path that has the guarantee that if you give me like a duality gap epsilon, then I can produce for you a path of solutions that go all the way from 0 to some fixed value, say capital T, that has the property that at any little t in between 0 and capital T, I'm at most epsilon away from the exact solution. So it's a very strong guarantee. And the idea is very simple. I just have it on these 2 slides, and maybe I'll just share it with you, and I think then we're out of time. You can take a look at this paper if you're interested for more details. The idea is just that we compute one solution at a particular value of t. Okay, let's call it tk minus 1. We just compute the solution at tk minus 1 using Frank Wolf. And we propose then to let t increase, but keep the solution, our proposed solution, just to be a constant over that interval. Okay, so t is increasing. We're at tk minus 1. And let's suppose that the actual solution was supposed to behave like this as a function of t. It just varied like that as a function of t. We computed the solution at tk minus 1. It was within epsilon of the exact solution. We're going to propose just to keep the solution to be a constant as t increases. I'm going to pretend like I'm going to use this as my approximate solution. What this path following method does is that it terminates as soon as the duality gap it sees between your approximate solution and the exact solution is bigger than epsilon. So terminate if this is bigger than epsilon, and then solve the problem here. Solve the problem at tk. And every time you solve the problem, you actually solve the problem at the accuracy level epsilon over m. So you solve the problem at a finer accuracy than you want to have as your eventual guarantee. That way you allow yourself some slack. So this method, it produces these values of t dynamically, because you move as far as you can before you have the duality gap being violated. Then you resolve the problem using, say, Frank Wolf. You move as far as you can. So then here we'd solve, again, we'd get like an approximate solution. We'd extend as far as we can until the duality gap is bigger than epsilon. And the solution path we return is just this piecewise constant thing, and has a very strong guarantee. Okay, so this can be effective for various problems, especially if you want a solution path rather than the solution under set particular values of t. This is sometimes called parametric programming. Okay, so that's all I want to say about Frank Wolf. I guess at this point you only have your homework left, so make sure to look at your homework and have a good Thanksgiving. I will see you next week.